of planning. There are some in this slide.
And thank you, Dr. Sridhar. Ready to go? Yeah, we are ready to go. Okay, perfect. Can the committee hear me online? Can everybody online hear well, especially the committee?
Yes. Yes.
Yeah, loud and clear.
Vishal, your video seems frozen for me. Is it the same for anyone else, or is it just me?
It's same for me, but I can hear him.
Yeah, I can hear
Is
him
it
as
better?
well, but it's frozen.
We also have, all right. So then we have Vishal's dissertation defense on generalized planning using language models and applications. Vishal is one of the successful PhD students that we have in the department. We're very excited to have him defending his dissertation. I'm personally super excited to see what he has to talk about. Now, before starting, Vishal, would you be okay if we ask questions from you as you're going, or you want us to keep the questions for the end? So I'm trying to finish in 45 minutes and keep 15 minutes for the question answer session. But if there are small questions that could be answered quickly, I'm very happy to take them as I go. So if there are clarification questions from the committee, we can ask it. Otherwise, we keep the questions for the end of it. So I think we're ready to go. We are in time crunch, I believe, so I'll let you go. Continue. Absolutely. I'll get started. Good morning, everyone. Just a second. Good morning, everyone. I'm Vishal Pallagani, and I'm here to defend my PhD dissertation on generalized planning using language models and its applications. My defense committee includes my advisors, Dr. Biplav Srivastava and Dr. Amit Sheth, and my examination chair, Dr. Rampton Sand, and Lior Horesh from IBM Research, and Dr. Sharath Sridharan from Colorado State University. In today's presentation, I'll start with the motivation and then introduce the thesis statement, then talk about the scope of this dissertation, the research questions that I have, and also what is already covered during the proposal. Then I'll focus on the research contributions, especially on how can compact foundation models be trained from scratch for plan generation, and how new generalized planners built using neural and symbolic approaches perform in real-world applications in two domains, in collaborative assistance, especially for information retrieval, and in smart manufacturing for replanning. Then I'll have discussions, basically summarizing the key takeaways, and also present some future directions, and end the presentation with my doctoral research journey. So planning tasks are everywhere, but they're hard to scale. Many real-world tasks can be framed as sequential decision-making problems. These include daily tasks like cooking, travel itineraries, dialogues, and procedural workflows, along with robotic simulations. These tasks come in diverse representations in natural language, for example, cooking recipes, and in semi-structured form, example is business processes and workflows, and fully symbolic, that is PDL domains. When we talk about structured planning, which is written in PDDL, it mainly captures this task formally in the form of actions, preconditions, effects, goals, and state transitions. And we have a simple toy example, which is called Blocks World, where there are two blocks on a table, block A and block B, and a robotic arm has to manipulate this initial state of blocks A and B and stack A on top of B, which is the goal state. So how we represent that in PDL is present as an example over there. But classical planners struggle for broad adoption, mainly due to requirement of manually engineered domains and also their dependence on the choice of heuristic and search algorithm to be used. If we use a wrong search algorithm, there is a possibility that the agent can get stuck in the environment. And if we use a wrong heuristic, it acts as a misguidance. And if we change the domain, the entire functionality breaks. So automated planning is conceptually powerful, but operationally brittle. And the dependence on domain models, search algorithms, and heuristics limit its usage. So in this scenario, why do we even want to look at language models? Language models essentially are powered by the transformer architecture, which consists of an encoder and decoder. And at scale, language models are shown to perform a plethora of tasks, including arithmetic, code completion, question answering, and so on. Just like all the other tasks, language models have been also applied to planning, but recent research has shown that language models can't effectively plan. So this raises the big question whether we should solely depend on general purpose large language models for planning. The answer is sort of being pushed forward in the recent years, especially coming from enterprises, that a single large language model is not a one-stop solution for all different applications. So as part of this thesis, I also want to emphasize and also look at specialized models with stronger inductive biases that can outperform general purpose large language models on structured planning tasks. So when it comes to generalized planning, especially in planning, we do not present a single problem, um, but we have a plethora of problem instances that need to be solved. So a scalable planning system must therefore avoid solving every problem from scratch and reuse and extract structure from prior experience. The generalized planning objective classically has been finding an abstract plan that could solve multiple planning problems. But with the advent of large language models and deep reinforcement learning, the goal has shifted towards learning one parameterized solver that transfers across many tasks from the same domain. The transition rules are shared across, but object counts, instances, and plan lengths can vary. So in this dissertation, I investigate how language models can be developed into generalizable planning systems. I specifically study how language models are currently being used in automated planning and how they can be adapted or trained to generate valid and coherent plans, and how neurosymbolic methods can integrate language models and symbolic reasoning to improve correctness and robustness, and how generalizable planners perform in real-world applications like collaborative assistance and replanning in a manufacturing environment. The scope of this dissertation distills down to 5 research questions, that is characterization of language models in automated planning and how the language models can be specialized for plan generation. More specifically, I look at how well do pre-trained language models, that is off-the-shelf existing language models, perform when it comes to plan generation, and also look at different model adaptation techniques that can help a language model perform better when it comes to plan generation. And the third research question is how can compact language models be built from scratch to support plan generation? And how can language models be used along with symbolic solvers to achieve robust plan generation via neurosymbolic architectures? And how do new generalized planners perform in real world domains? So what I have already covered in the proposal is basically RQ1, that is the characterization of language models in automated planning, where we did a survey of uh, recent literature around planning and large language models and created a semi-automated way to categorize all these papers into 8 specific categories, where we saw that there is a category drift as we move from year to year. That is how language models are being used for planning is changing over the period of time. And I also talked about RQ2, that is how can language models be used for plan generation, both in their pre-trained form and also uh, when they undergo model adaptation techniques like fine-tuning and prompting approaches. Then I also covered RQ4, which is neurosymbolic architectures for plan.
I'm the PhD defense.
uh, Neurosymbolic architectures that support plan generation. And the neurosymbolic architecture that I talked about was SOFI, which was inspired by the thinking fast and slow paradigm of Daniel Kahneman. And then we evaluated this architecture on classical planning domains, and the results were what was talked about during the proposal. In this particular presentation, I'll cover the pending research questions, which is how can compact foundation models be built from scratch for plan generation, and how they perform in real world applications. One real world application was also covered during the proposal stage, which was called as Prudent, which is a conversational agent for information retrieval that flexibly mixes both planning and reinforcement learning. So moving on to the research question, which is how can compact foundation models be trained from scratch? Before I get started, I want to formally introduce the planning setup. We study planning over a state transition system, which consists of states, actions, and a transition function. And a planning task here is given the state transition system and an initial state and a goal state. Our planning task would be to find the plan, that is a sequence of actions that solve for the given goal when we start from the initial state. This is an example where again we have two blocks A and B on the table, and the two actions that I need to perform in order to reach my goal state is pick up the block A and then stack A on top of B. So the generalized planning objective I introduced earlier as well. That is, we want to learn one parameterized solver that can solve for many instances from the same domain. And why it is a difficult task is the state description grows with more number of instances or objects, and object names can be arbitrary. So permutation invariance is a needed technique, and plan horizons can also increase on large instances. So the generalized planning objective is have more number of objects but still be able to solve them. And even if the object names change, we should still be able to solve them. So permutation invariance is what we need as an inductive bias in our model. And recent neural approaches for plan generation are action centric. That is, they model the probability of a plan given the planning task over the product of time over action space, or a policy which generates a distribution over the actions given this initial state and the goal state, and they directly predict the next action sequence token. Representative examples of action-centric planners include Plansformer, which was the fine-tuned Code T5 model that was covered during the proposal, and there have been other recent works as well, which include PlanGPT, which is a GPT-2 fine-tuned model, and symmetry-aware transformer, where the transformer architecture itself is tweaked to do plan generation. However, these models, especially what was seen in Plansformer, is they failed to completely generalize to unseen domains, and this exists across all action-centric approaches. So when we say we want to train a model that can do plan generation, what are the inductive biases that we are looking to enforce? That is, we want to have explicit world state evolution. The model should know how the state changes, and we want to have sparse local effects as they model the strips conditions of add and delete predicates. And we want to have a size invariant structure, that is, execution should remain inside the valid successor set of the domain. And we also want to have symbolic validity to avoid any hallucinations, but to generate actions that actually respect the planning domain environment that was defined. And some of the related works in this field where learning is used for planning, we start with action-centric neural planning that I was just describing. Their main core strength is sequence modeling, and they're also easier to train once you have large amount of data, but their core weakness is that transition dynamics are only implicit. Then there has been studies on using graph-based state representations as well, like strips HGN and Boost, which were used for heuristic learning and not directly generating the end plan itself. And they show that having a relational graph structure is highly effective for getting the right heuristic. And we borrow that insight in our work on state-centric planning. Sorry. Yeah, and there is work to show the importance of having symmetry and invariance as the inductive biases while training a model, especially GNN-based planners and symmetry-aware transformer or SIMT emphasize permutation invariance and object symmetries. This motivated us to focus on having symmetry invariance and also being size invariant when we are designing the embeddings for the state-centric learning approach. And there have been hybrid and model-based approaches. One example here is LLM modulo, and previously in the proposal, I showed the architecture for PlanSophi. They use system ones, or they use language models in tandem with symbolic solvers to generate plans in coordination. So coming to the proposed approach of state-centric learning, we directly predict the next state given the current state and the goal, which is different from the action-centric learning, where the next action is directly given as output. Instead, we predict the state as an output. And in practice, we do this in a learned representation space where the model updates the current state embedding based on the goal. And this is implemented in a residual update. So the model focuses on predicting what changes in the state, And this mirrors classical strips formulation or transitions where actions correspond to adding and removing of facts. The key challenge here then becomes how to represent the states so that they are invariant and also relational. So for each state goal pair, we construct an instance learning graph capturing objects, live state variables, and goals so that the state is represented as a relational structure rather than a flat vector. If we look here with the same running example of block A being on the table and block B being on the table, A and B are my objects which are captured in the instance learning graph. And the goal fact is to have A on top of B, which is also captured in the instance learning graph. And then we have the state facts, that is the current state in which the environment is present. A is on the table and A is clear to be picked up by a robot arm. The robot arm's hand is currently empty, which is model, and B is clear and B is also on table. And how all these facts are connected to each other is what is represented in the instance learning graph. And the most important thing that the instance learning graph has is node features or FCAT that is present in the tuple. So FCAT shows us which particular predicate is live and whether it is required in a goal or it's not required in a goal. So that is what we represent with APN, UPG, and there is also APG, that is the state is true and also required in the goal. We currently do not have that in the setup, so that is not annotated. Once we have the instance learning graph, we apply two base failure layman refinement steps where node representations are iteratively updated based on their neighbors and edge types. After refinement, we aggregate these into a global embedding by taking a histogram over the refined colors, which summarizes the distribution of local relational patterns in the state. This gives us permutation invariance, size invariance, and strong relational expressivity. We also compare the WL or relational state embeddings against a baseline called fixed slot factored or FSF. And FSF encodes a state as a fixed length vector where slot 0 stores global facts and each subsequent slot corresponds to a specific object under a fixed ordering. Within each object slot, it, its properties are listed explicitly, and for the goal information, we use special sentinel values. If a goal fact is specified for an object, we write -10 in that cell. It means this is what we want, but it has not happened yet in the environment. You can see that in slot 1 for A, the goal entry is -10, and for slot 2, object B has no direct goal constraint in this problem, so we write -99. That is just padding to keep the length, vector length fixed. While this representation is simple and direct, its key limitation is that it depends on a fixed object ordering, making it sensitive to object renaming. That is, if I change my objects A and B to X and Y, then the output vector that I get completely changes, which is a problem that WL encoding previously solves. And these two are the embedding processes, and in between happens the model training phase, but at inference, how do we use that model is what I want to cover as well. So at test time, we do not execute the neural prediction that is coming out of the model directly. Instead, we use it to guide a symbolic decoding step. And this is the contribution of the neurosymbolic approach in this setup. So given the current state, the model predicts a target embedding for the next state conditioned on the goal. So it tells us where we want to go in the representation space. We then enumerate all valid successor states under the domain dynamics and then select the one whose embedding is closest to the target. In other words, we project the neural prediction onto the set of valid states. The executed action then simply becomes the action that actually gave us the successor, that produced the successor. This turns the model into a planner of sorts rather than just being a predictor like what we saw in the action-centric works, where the action is directly being predicted and it could violate the domain dynamics and also hallucinate. Here, every action is valid and all intermediate states are valid as well, and the prediction errors are corrected online through the projection step. This is the overall pipeline. I'll talk about the pipeline in detail, but on the outset, we have data generation. Then we have the encoding, which we covered, that is WL representation and FSF. Then we have the modeling. We use two different models, LSTM and XGBoost. Then we have the plan decoding that we just looked at, which is neurosymbolic in approach. So the if we see how the data is being converted into training trajectories. Step one is plan generation. We use fast downward with A star and LM cut heuristic under a 60-second timeout to generate plans for the training set. And if that fails, we fall back to a greedy best first search with FF heuristic with a 300-second timeout. Once we have the problem, PDL domain, and the generated plan, we use a plan validator, which is an existing tool called as val, in verbose mode to reconstruct full state trajectories. So what val does is takes the three inputs, planning domain, problem, and the plan, and generates all the state transitions that happen in between of reaching the goal. And finally, we convert the states into embeddings using WL and FSF. And if we look at the domains that we are using, these correlate with the previous domains that I had during the proposal with one new addition of Visital. And we have blocks called Gripper and Logistics, and all these are classical IPC planning domains. And there are values given for the train set, the validation and interpolation and extrapolation. And you can see that the training split uses only small instances. The validation measures nearby generalization, and interpolation tests unseen in range configurations. For example, in train, we have for blocks called 4, 6, 7 block configurations as part of the training, and we have 9 training uh, data points. So when it comes to interpolation, we are testing on planning problems from blocks world, which have 5 blocks as the environment. And extrapolation is the key test object that we are going for, which shows us if the model is actually being able to generalize. So we have object counts in extrapolation set quite large compared to the training set. And one more thing I want to highlight here is how small the data set is when I have to talk about Transformer as an example for state-centric, because that was covered. We used 80,000 data points to train that model. And here we have only for Vistol, it is 207, but for everything else, we have less than 20 data points. So coming to the model families that we are using, we chose LSTM and XGBoost. LSTM has 2 recurrent layers with 256 as the hidden dimension. And input at each step is the concatenation of both the initial state and the goal embeddings. This is designed to test whether the temporal memory helps model state transitions effectively. And when it comes to XGBoost, it's multi-output regression. Its input is a flattened tabular vector built from the state and goal embedding, similar to the LSTM model. And it is primarily designed to test whether local transition learning is sufficient without having the requirement for sequential memory, which LSTM has. Then we do 2 modes of prediction with these models. One is state mode, that is the entire next state is constructed as an output, and we have delta mode, that is given the current state and the possible future next state, what is the difference that has happened in the environment? That is what the delta mode produces as an output. So LSTM with state mode prediction uses cosine embedding loss, and LSTM delta mode with delta mode prediction uses mean squared error as the embedding loss. Whereas XGBoost for both the state and delta use MSE or mean squared error as the loss. We use cosine for states because only direction in the embedding space matters, and MSE for delta when we are using LSTM because they represent actual displacements where magnitude matters. XGBoost uses MSE throughout since it operates in a fixed and scale sensitive feature space. So the primary empirical findings are as follows. I'll quickly explain what the columns mean. FD is fast downward, which is a classical planner running under a 60-second timeout. And all the models are being run under a 60-second timeout to keep the comparison fair. And plans, the second column is Transformer, which is fine-tuned code-T5 model for plan generation. And Plan GPT, which is the GPT-2 based model. And uh, then we have symmetry aware transformer with an encoder only, which is on the top you see a SymTE, that is symmetry aware transformer with encoder only, which actually predicts a heuristic and not the output action directly. Then we have symmetry aware transformer with an encoder and a decoder, which predicts the action as output directly. And all these are one category, which are present in white, which are previous implementations that already exist for us to use as a baseline. Then the grayed out part of the columns are the different model combinations that I just mentioned. We have WL encoding with LSTM model, WL with XGB in both state mode prediction and delta mode prediction. The same goes for FSF with both the model combinations and mode combinations. Then we see that transformer and plan GPT variants are at zero on extrapolation or close to zero on extrapolation in all four domains, whereas symmetry aware transformer, which actually changes the transformer architecture and fixes and brings in some invariance properties, shows non-zero extrapolation in blocks called Gripper and Vizsla, but it fails in logistics. Our best state-centric models exceed symmetry-aware transformer in Bloxford and Visital, and I'll explain why it is very significant for us in the next few slides. Gripper is the strongest case for action-centric recurrence and symmetry-aware modeling that SIMT actually employs as part of its training paradigm. And if we closely look at the extrapolation behavior and ablate based on the representation, FSF-based models are essentially unable to extrapolate well, whereas WL-based models achieve positive extrapolation in three domains apart from logistics. Uh, this shows that size invariant relational structure, the whole hypothesis that we started with, is actually necessary and it's not an optional requirement. Then if we ablate based on the model types, delta modeling improves XGBoost strongly in sparse strip domains, whereas LSTM helps when trajectory level dependencies matter more, especially in. So I previously mentioned that with the models that we have trained, the best performance is close to symmetry aware transformer, or sometimes in some domains even better than symmetry aware transformer. But it is very interesting because the sample and model efficiency for the models that we have used is way smaller compared to what the transformer based approaches employ. The LSTM models use about 1.1 to 2.1 million parameters, and XGBoost uses about 128K to 819K tree nodes, whereas SIMT is roughly around 25 million to 35 million parameters. PlanGPT is 125 million, and Transformer is 220 million parameters. The proposed models, that is combinations of LSTM and XGBoost, achieve 50% strict extrapolation success in Bloxworld and 100% in Visital after training on only 9 and 207 problem instances, respectively, whereas action-centric models like SIMT require thousands or tens of thousands of training data, especially with augmentation, because it's harder to get that kind of training data using IPC planning domains. And PlanGPT and Transformer are also in the same boat, along with symmetry aware transformer. One interesting failure case from this entire study is logistics, where the extrapolation is zero compared to all the other three domains that we have. And this is due to the fact that logistics contains deep hierarchical coupling across object types and transport modes. So the approach that we adopted of having one-step local successor prediction during the inference stage is not sufficient to preserve the necessary long-range dependencies that we need while generating plans for logistics. So to conclude the state-centric learning work, we first introduce a new state-centric learning approach for plan generation, and we show that compact state-centric models can match or even exceed large general-purpose models, which are based on action-centric learning. And we also identify limitation, especially coming from the logistics domain. And we also know that representation choice is very crucial. That is, WL or relational encoding has way better performance when compared with FSF as the baseline. So the follow-up question here is not what representation choice we need to use, but what tokenizer gives us that representation choice to better model the state-centric learning pipeline in order to achieve better plan generation. So as a natural extension, we look at what are the different tokenizers that we can use when we keep the rest of the pipeline fixed. That is, our input still is an instance learning graph. And now what kind of tokenizers can be employed along with the instance learning graph that gives us better embedding space for the rest of the models to work on. So what we are changing is the state encoding, the modeling and the plan decoding remain the same, and the data set also remains the same. And this is very important because tokenizer helps us generate the embeddings, and embeddings go and get used for model training. So even if we have a superior model, they cannot reconstruct what is already missed by the tokenizer. So we need to have a better tokenizer to begin with, and the model training can benefit from it. So we looked at a WL before as now I'll talk about the 4 different choice of tokenizers that we have for this work. WL is coming from the previous work as a baseline, which we have seen the functioning of. And WL also showed us how local neighborhoods play an impact in performance. On the right side is the shortest path graph kernel. So instead of focusing on local neighborhoods, this approach captures global structure. We compute all pairs shortest path distance using breadth first search on the interaction graph, or the ILG that was constructed and being passed as input. Then we build feature histograms over triples of source node, label, and target node label, and their shortest path distance. If the two nodes are disconnected, then we assign them a special infinite distance bin. The representation of shortest path graph kernel preserves global reachability and path geometry, which can be important when long-range dependencies matter more than local patterns. The third tokenizer that we looked at is GraphBP, and this is a tokenizer that is inspired by white pair encoding from the NLP literature. So we first, since our input is a graph, we first have to serialize that graph. So we use the DFS approach to serialize our input graph. And this gives us a sequence of tokens, which we can then compress using the byte pair encoding merges learned from the training data. The result is a domain-specific vocabulary, typically on the order of 100 to 500 tokens. One advantage of this approach is that it can capture recurring structural motifs like common predicate co-occurrence patterns or cycles that exist, and how because we linearize the graph, we lose the strict permutation invariance and some relational symmetries that may be obscured. On the right side, we have the final tokenizer, which is SymHash, which takes a very different, highly compressed approach. Each node is represented by a feature vector that concatenates one hot encodings of predicates and argument positions. These node features are then summed across the graph and projected using a fixed transformation matrix, followed by a sign function to produce a compact binary code, uh, which has 256 dimensions. This makes SymHash extremely compact and efficient, and also permutationally invariant. The trade-off with SymHash, however, is that it has a lossy representation, so it can blur fine-grained structural differences between similar states. Then moving on to the implementation details, these remain exactly the same as we have used for the previous set of experiments. And the tokenizer specific hyperparameters or the implementation is mentioned here, which I sort of covered in the previous slide. And the metric that we are using is the amount of plans from the test set that we are solving. So the primary empirical findings look like this, where WL is the only tokenizer which has non-zero performance in terms of extrapolation across all the 4 domains. And especially for Bloxworld, WL is the only tokenizer which provides any values, and all the other tokenizers have a zero when it comes to extrapolation or interpolation or even validation accuracy. And SimT's best performance in Bloxworld is 13% of plans being solved on extrapolation. So when I have SimT, the best performance, it is on the extrapolation set and what is the best across all different combinations of SimT, both encoder and encoder decoder. Then Wisdol is dominated by WL and shortest path. But if we see shortest path across all the combinations of both model and mode, that is LSTM in state or delta prediction and XGBoost in state or delta prediction, achieves the same performance of 87.2%, which is the highest across all combinations. And WL achieves that with a specific combination of XGBoost plus delta, and the performance drops to as low as 3. When LSTM plus delta is used with WL tokenizers. When it comes to Gripper, symmetry over transformer remains the strongest at 79% of plan solved. And GraphBP, among the 4 different graph-based tokenizers that are used, the best performing is GraphBP in comparison with WL. So in Bloxworld, I mentioned about the importance of WL and how all the other tokenizers fail. This is because of the local 2-hop stacking motifs that determine valid successor structure, which WL provides. And when it comes to Gripper, where GraphBP is performing the best among the 4 tokenizer choices that we have considered. This is consistent with a domain driven by recurring pick, carry, drop, return co-occurring patterns. And when it comes to Visital, shortest path performs the best because it consistently shows the highest percentage achievable in that domain, whereas WL has only one instance where it achieves 87.2. And logistics still remains an issue where no tokenizer wins, again, because of the one-step dependency that we are using in inference that is not fixed. Next, if you look at the interpolation and extrapolation gap, we see that shortest path on Visital, which is SP, drops from 100 to 87.2, and the same applies for all the domains across all combinations, where interpolation is higher and the extrapolation performance drops significantly, especially on logistics. The interpolation is at 88.9 percentage, and it drops all the way to 0% when we are increasing the number of objects by a huge margin. So this clearly shows us that interpolation-based validation is not a reliable metric alone for choosing the tokenizer. And we also see that the tokenizer must be chosen based on the domain type and have the structural alignment with the domain so it performs better. Then moving on to the model sensitivity, when we look at graph BP and SimHash, they clearly perform better with LSTM as the model choice compared to XGBoost. And shortest path is the most robust. If you remember, on Visital, shortest path has 87.2 performance across all the model combinations, and it actually retains that throughout all the different domains as well. So even though the performance is not very high, shortest path has very negligible difference when the model is being changed or the mode is being changed. And WL is highly mode sensitive. So on Visital, we have XGBoost reaching to 87.2, while XGBoost plus state drops to 8.2 when WL is being used. So as a conclusion, the tokenizer structural scope predicts domain suitability, and we have to choose different choices of tokenizer can give a yield completely different results based on the domain that we are employing it for. And hierarchical domains still remain unsolved. Also, we did not fix the problem that we previously identified. We wanted to study and isolate the effect of tokenizer. So logistics still has 0% when we are using different tokenizers. Future work in this space could look at hybrid tokenizers and also using learned graph encoders, so the embedding space is much richer, and have hierarchical transition models as well, rather than treating the representation and dynamics separately as we did currently. So the training procedure, if we look at from my presentation so far, we manually choose the choice of search algorithm and the choice of heuristic, and we use different time limits in order to be able to generate plans well. But IPC or the international planning competition has a wide variety of plans. So can we use this kind of knowledge that is available and have a structured metadata which can tell us or guide us in what planner can help us solve a particular problem? This essentially helps us back in creating a richer data set or even a larger data set. And we can also organize this data set in a curriculum learning kind of fashion. So the learning happens stepwise and the model performs better. So as part of this, we also looked at having a formal symbolic representation of the knowledge from the IPC domains in the form of a planning ontology. And an ontology is a structured and formal representation of knowledge that captures concepts, relationships, constraints within a specific domain. So it is not that there in the research community there are no ontologies when it comes to planning, but most of them have been domain specific ontologies, and they do not capture the concepts and relationships describing the nature of automated planning itself. So what we try to do is build an ontology that captures these relationships. And our ontology is composed of 19 distinct classes and 25 object properties. And these are the 10 competency questions that guide this ontology. There are two use cases that we have primarily explored when we build this ontology. One is identifying the most promising planner for a given planning problem. So how we do that is we have an ontology policy where we use Sparkle queries to reason about the given problem. And historically, what solver has performed the best when we solved a similar domain is what is looked at using Sparkle queries. And we have a random policy where we randomly choose a choice, randomly choose from the planner choices that we have at hand. And we see that ontology policy helped reduced the search nodes and also improved success rates in harder domains, outperforming the random policy. We also look at a second use case with the planning ontology, which is explanation generation, where the planning ontology is used to generate plans summaries and explain specific or non-selected actions. The type of explanations that we provide are basically in three categories, which is present in the table: plan explanation, and explaining why a specific action is picked, and also explaining why a specific action is not picked. This is also done with the help of Sparkle queries. And the natural language generation aspect of it is template based approach. We are not using an LLM to verbalize it a lot. So we also conducted human experiments to evaluate how well they're able to understand the explanation that is generated. And we collected 10 responses on a 1 to 5 Likert scale, which showed the preference around 70% for the explanations that are generated. Once we have, I mean, another offset of training a model and only evaluating on plan generation is problematic. We also need to see what are the other use cases that this model might have. So we need to have an auxiliary task to evaluate such a trained model that could do plan generation. So we tried to build a benchmark, which is basically called as plans, which is plan summary of planning like tasks. Text summarization is well known. There is summarization for news articles. There is summarization that exists across, and it also has business use case. But many real life tasks involve generating a series of actions to reach specific goals, and we refer to them as planning like tasks. These include, as said before, cooking and travel. And actually, in real world, we already have an example of what a planning like task summary looks like. When we go to Google Maps and we set a source and a destination, the different possible set of routes are summarized based on the time it takes, the interstate that we have to use, and we make informed choices based on this high level summary. And if we select a certain choice, then we have a whole set of actions. So we formally define the plan summarization task as having a set of different plans which consist of actions by themselves, and we want to generate a summary based on some constraints like length and the number of actions to be used as part of the summary. And we use the plants benchmark. The plants benchmark is basically made up of three domains: automated plans, recipes, and travel routes. And we have 10 problems each per domain. And per problem, we have 5 each from automated plans and recipe domains, and 3 for travel routes because of the limitation of the API that we have used of OpenStreetMap API to output the amount of plans. We have 3 different benchmarks. An LLM, GPT-4o, text rank for extractive summarization, and a frequency-based baseline. And the performance looks like this. The baseline produces summaries which are mostly of similar length, whereas text rank has the least median out of the three different approaches tested. But the variation in the plan in the length of the generated summary is a lot, whereas GPT-4 has the highest median of generated summaries, and uh, GPT-4o is more lexically diverse. So we see that reflect in the user study as well, where users prefer the summary from GPT-4o as it is more understandable. So moving on to the applications, we so far looked at how a custom model can be built from ground up. But if we move on to the application of generalized planners in real world domains, we start with collaborative assistants, where currently if we ask LLMs or chatbots like ChatGPT certain questions related to politics or HIV, which are domain sensitive, we either have to verify the answer manually or ChatGPT denies answering such questions, especially when it's from politics. So the goal here is to build conversational IR systems that are risk aware and are also traceable and return to either grounded generative answers, like having an FAQ document which provides grounded answers from us, and explicit do not answer strategy where we do not want to answer dicey questions or harmful queries from the user. So the problem formulation here is to have a domain of answerable questions from a trusted FAQ which is validated, and also have a generic domain independent interaction such as greetings and closings. And we also have a domain for not to answer questions or do not answer strategy. Then the response modes include to answer directly from the FAQ or have an explicitly verified answer or respond with a do not answer strategy. So this slide shows the metacognitive logic that I previously explained in the relation with SOFI when it is used for plan generation. We aim to adopt a similar metacognition strategy when it comes to chatbots and information retrieval as well. So the domain that we have tested the chatbot is with a use case on HIV discourse. So there are 47 UNAIDS HIV FAQ that we have accessed, and the S1 that we use is Llama, and the S2 is SafeChat, which is again built by the group. Um, and it is a RASA-based approach which provides grounded answers. We tested a total of 47 question answer pairs, and 43 of them were classified as safe interactions by Grenade Guardian, which is a LLM fine-tuned to predict harm on various categories, which is present in the table on the top. So out of the remaining four, one harmful question but safe question answer pair, and two safe question but harmful question answer pair, and one harmful in both conditions is found. Moving on to the application in smart manufacturing, we consider a multi-robo rocket assembly line, which is actually deployed in the future factories at the University of South Carolina, which has about 40 to 60 coordinated steps where faults like mistakes, jams, or overheating can occur at any point. The standard approach here is to separate planning and recovery. There is a planner that handles nominal execution, and faults are handled by a rule-based system outside the policy. The problem with this approach is that the planner is completely unaware of the faults. It cannot reason or risk or optimize for robustness. The deeper issue, however, is that the faults themselves are heterogeneous. Different faults require different intervention strategies and lead to different future states. This creates heterogeneous backup sets where the transition structure itself changes depending on the fault type. And because of this, recovery cannot be captured by a single fixed strategy or a rule-based system. Becomes very brittle and hard to scale. Our key idea to propose as a solution is to model faults themselves directly inside the MDP. Instead of treating them as exceptions, we incorporate fault probabilities into the transition function, encode fault information in the state, and include recovery actions in the action space. So there is a large body of work applying reinforcement learning to production control, especially in domains like scheduling and dispatching. However, all these approaches handle faults outside the learning loop, and the action space remains static across all the states. Separately, anomaly detection itself is an independent large body of work that focuses on identifying faults, but they do not try to learn to overcome these faults. Classical MDP planning provides a strong decision theoretic foundation, but it relies heavily on tabular representations and does not scale to heterogeneous fault settings. And action masking in RL is especially looked at in games, and it is theoretically sound, but it has not been applied to fault recovery in smart manufacturing systems. When we look at these areas collectively, a clear gap emerges. No prior work simultaneously models fault transitions inside the transition function or encodes fault information in the state and learns recovery actions within the action space. Our approach brings all these three together. The policy observes the active fault through the state, selects only valid recovery actions through the action space, and accounts for their cost through the transition dynamics. And the learning happens in an online RL setting, and we have built a simulator to actually mimic the future factories setup. The blue tiles that are present in the simulator are where the robotic grippers are placed, and the top two on the second column are R1 and R4, which basically either pick up the tray or place the tray back once the rocket is assembled. So we do not consider them while training of the model. And R2 and R3 are the actual robotic grippers which handle the building of the toy rocket. And we have four fault families, which are the pickup itself is failed by the gripper and the tray gets stuck on the conveyor, or there is a missing piece, and there is also overheating of the conveyor belt. So This DQN and AVI are well-known models, and this slide focuses on how we adapt standard training algorithms to the setting of fault recovery. Both DQ For DQN, the first change is action masking. We prevent the agent from selecting invalid actions by assigning negative infinity to actions outside the valid set. And we also include fault metadata in the state. This allows the policy to identify the active fault and select the correct recovery behavior. Uh, Thirdly, we have the replay buffer that accumulates fault experiences over time. And the fourth change that is made is fault penalties propagate backward through Bellman updates, and this makes the learned Q value risk aware, reducing the preference for actions that are likely to lead to failures. And when it comes to AVI, the most important change is in the transition model. All fault outcomes are explicitly included in the transition function. This means that the value function inherently captures the expected cost of all fault tolerances. And in addition, we also apply reward shaping, so the training happens faster while preserving the optimal policy. This slide shows the main results in the smart manufacturing replanning setup, evaluated on both known, which is the top table, and unknown faults, which is the table below. For known faults, we run 60 episodes and measure success rate, first recovery action, which is FRA, and recovery latency, which is the RL. And all learned methods, DQN and AVA, achieve 100% success, matching the scripted baseline, uh, which is random, while the random baseline is below 5%, confirming that the task is actually hard to solve. The difference comes, however, in recovery quality, where AVI outperforms DQN with higher accuracy and lower latency because it uses exact fault probabilities, whereas DQN estimates from sampled experience and underrepresents rare results. Scripted plus BFS cannot be evaluated on these metrics since it follows fixed rules. And when it comes to the unseen fault, both learned methods still generalize. AVA reaches 89%, while DQN reaches 84%. But the scripted method fails because this rule is not present in the previous part. And if you want scripted BFS to still work, we have to add this explicit rule and then test the model again. So there is no generalization happening when we use the existing approach of having a rule-based way to handle the faults. Whereas if we use learned models like DQN or AVI, there is a possibility that we can still handle unseen failures. The key takeaway here is that learned approaches adapt to new faults with minimal changes made to the MDP, while rule-based systems require manual re-engineering. This basically concludes my actual research contributions. I'll quickly summarize the key takeaways. So when we start, when and this is summarizing both proposal and the current presentation. So the landscape of LLMs in planning is very broad and it's also evolving. That can be seen with the category drift as well that we identified. And pre-trained LLMs by themselves are insufficient for reliable plan generation. Model adaptation techniques for these LLMs help them push the boundaries of generating valid plans to some extent, but still there is problem of hallucinations and there is problem of not being or not being able to generalize to completely unseen domains. Then we introduced a state-centric learning, which offers a fundamentally different training paradigm for plan generation, where compact models can can match or outperform the performance of large transformers when it comes to plan generation. And we see strong extrapolation from minimal training data, and we also see 3.5 times improvement on planning performance when we consider the best models and place it against symmetry of a transformer. We also see that tokenizer is a critical choice to be made in such scenarios. And in neurosymbolic integration, which helps in turning unreliable language models for plan generation to robust planning components, and in neurosymbolic planners where the real world deployment is actually feasible and also performs better. So the future scope, if I have to go research question by research question, the first was on characterization and literature tracking. We currently had a keyword pipeline with human refinement in the loop, but a better classification approach can be adapted, where LLM-based models can be used for categorization of the research papers and to come up with these categories. And there can be richer tracking as well. We currently do it across categories, but within category, we can also look at planning formalisms, how LLMs or what LLM families are being used, and what are the evaluations protocols specifically. Is coverage being used? Is plan validity being used? And so on. And moving to plan generation and state-centric models, uh, we can look at hierarchical transition learning, which can help us solve domains that are currently challenging, like logistics. And we can also have adaptive tokenizer selection, as currently the tokenizer is a manual choice that is made, and we have to perform multiple experiments. And the domain performance on a certain planning domain is based on the tokenizer choice. So if we have a way to do the tokenizer choice in an adaptive fashion without actually having to run different experiments, that would be a good to have. And scaling to continuous domains, we currently look at deterministic classical planning problems, but there are numeric planning problems and a whole set of uh, other venues where these models can be looked at. And in neurosymbolic integration, if we look at, there are different parameters like T1, T2, T3. This has come up during the proposal as well. All those parameters are currently manually set, but having an approach where the parameters can be manually tuned for a certain domain is an added advantage and is a future work. And when it comes to applications, SafeGen Chat currently handles safe discourse in text, but that can be extended to multimodal inputs as well. And when it comes to the manufacturing replanning pipeline, it is currently trained model, but what we are looking at is actually transferring to the robotic factory that is there in the future factories. And my coming to the doctoral research, how much time do I have? 3 minutes, 5 minutes. Okay. And first, I would like to thank my advisors, Dr. Biplav Srivastava and Dr. Amit Sheth, for giving me the opportunity to do even PhD. Dr. Amit Sheth was the first one who gave me a chance to even come to the US and do research in very different setup than what I was used to in India. I was doing BTech. I did not have a master's, but he believed in me and gave me an opportunity to do my PhD directly after my bachelor's. And I think I'll I'll remember that for a long time. And Dr. Biplav Srivastava introduced me to the world of planning. When I heard the word planning in my first call, I thought professor was telling me to plan ahead and maintain this. So I had to go to Wikipedia, and there was not much information. And finally, it led to the work that I did today. So I'm really grateful to both of them and to all my committee members. I know the invite was very last minute. I shared the information last minute, but all of you have agreed to be here, and I'm very thankful for that. And if I was introduced to research at all, that is by Dr. Venkanna when I was at IIIT in Raipur as a bachelor student. My first research paper was with him, and that is still the most cited research paper. I'm not sure how, but so I'm very thankful for Dr. Venkanna to even showing me that there is this option, and I need not change. I need not change the job placement or something to be my next adventure in life after my bachelor's. And to Francesca and Kirti from IBM, who mentored the entire SoFi pipeline throughout for me. They helped me build the architecture. Kirti especially helped me ideate on the different experiments, helped me make submissions to different conferences. And this is a picture from, I think, this year's AAA, where we had a tutorial and a hands-on lab on SoFi and another extension of SoFi in a different domain. So a large body of work that was done at IBM. And I did not add Leo's name here because Leo is already there, but huge thanks to Leo as well from IBM. And to all the members of the group, both past, new, and current, um, thanks to everybody who was part of lab. Uh, Manas's photo, especially because he was the mentor and guide during the internship stage that, and finally moved to joining as a PhD student here. He was a guiding light during that period of time, and a lot of my colleagues who helped me with everything throughout these last 5 years. And to my parents, they're coming at a very later stage, but I thought I had to thank all the previous people who actually played an integral part in my PhD journey. My mother I was talking to my mom on the phone today morning, and her way of giving confidence to me was that she recited 10 poems when she was in 10th standard without stopping anywhere in between. And she was like, it's the same thing. You have to just speak what you know. So I, I think that from there to here, it's a journey that I cannot imagine, and it's very overwhelming at times. And to my partner Kirti, who has been a great support for the last 2 weeks, especially uh, because I was working on the presentation and everything, so there was a lot of confidence boost that I received from her. So thanks for that. And that is me, Vedant, and Bharat, who are currently here. This was 10 years ago. We were all BTech colleagues, and now we are colleagues. But Bharat is here. This was Bharat before he had the PhD problems, and he still had hair. So, so that was 10 years ago, and they have been doing all the. They are my roommates as well, so they have been taking care of a lot of things, so I can focus on my work. So, huge thanks to all of them who have helped me put this forward. And as a summary of what has happened throughout my PhD journey, I had the opportunity to mentor 5 students. Two of them were from India initially and helped me actually build the Transformer work and develop a website and deployment of the Transformer work. One of them is currently leading a startup, and the other is currently at CMU. And there is Riju, there is Nitin. Nitin is not here, but Nitin helped shape the entire work around state-centric planning. He had the opportunity to to go to ICAPS this year based on a paper that we previously submitted to ICAPS that got accepted, and he attended the talks and he got some inspiration, and the entire state-centric learning work has revolved around that. So very thankful to all of them. It's not me telling them as well, but it's equally them working with new ideas and coming up with new ideas. And for industry research internships that I got to do at IBM and learn a lot. I also had an opportunity to file 6 patents again, thanks to Dr. Srivastava, who has pushed that patent, who has made the process easy for us, rather, I would say, because patents or even papers at some point was a huge thing for me that only highly intellectual people did. So getting to do some of that as part of this PhD journey is something that I'll cherish forever. And not 2 labs, actually, we did 3 labs, all at AAA, tutorial and a hands-on lab. And I also got the chance to be a founding student committee member at AAA, and I quickly scroll through all of that. And these are the patents, but previously I had the set of publications. Thank you so much. If there are any questions, I'll be happy to answer.
Well, wonderful. Let's get
Thank you,
is our chair of the committee there? Otherwise, we can just basically ask the audience to ask questions.
Yes, sir.
From an audience usually, so I don't have any, but they'll have. But ask questions if you have any. So Vishal, I have a question for you, or a comment. You have listed a lot of work. Okay, can you just summarize which work you led and which work others led and you contributed to them?
Absolutely. I'll go to the.
You can go to the outline.
Yeah.
Whatever the thing is, right?
Research questions. Okay, so the characterization work is something that I led closely with the help of Nitin and also other people in the lab. The initial work that we did had a lot more collaborators. This included people from IBM. This included Dr. Sheth, his group students as well. I mean, of which I am a part too. So the first work was a very larger effort because we had around 126 papers people were going through and manually categorizing. The later part of the effort, where we created a semi-automated pipeline, is a joint work that I led but collaborated closely with Nitin and Professor Srivastava in getting that paper out. And the second, how can language models be used for plan generation, where we look at modal adaptation and all these other techniques to improve the plan generation performance of language models. I led that effort, but in close collaboration with Bharat here, and also people from IBM were involved. And the compact foundation models work was led by Nitin, and I closely worked with him. And the tokenizer part of the work is what I led. And when it comes to integration, this is a work, the architecture was already pre-existing. The using of the architecture for planning is a work that I led, and also built a tool around how SOFI can be used for any domain and can be installed, that we did the AAA lab on. That is again a part of the work that I pushed on. Then finally, in collaborative assistance for information retrieval, there have been a wide list of contributors for this. I think all of the group was at some point involved in this, but the prudent work was my initial work when I joined PhD, and that is something that I did. When it comes to Safe Chat and Safe Gen Chat, this is a collaborative effort, mostly led by Kaushik, and at times it was led by Bharat, and I was involved in the initial stages. And when it came to Safe Gen Chat, where SOFI has to be used in tandem with Safe Chat, I stepped in to support John. That Safe Gen Chat work, however, is led by John Iden, who is again currently doing masters, but he was involved with the group since he was a bachelor student at the university. And when it comes to manufacturing for replanning, the whole, again, this is a whole body of work, but the RL part was led by Vedant, and I worked closely with him. But the overall manufacturing pipeline, anomaly detection, and everything was heavily led by Chetrangi. I think most of you were here to look at her proposal as well. It is centered around that, and she worked closely with future factories and pushed the boundaries of using AI techniques for manufacturing. But replanning is something that Vedant and I closely collaborated on, and it comes to using RL for replanning. Yeah, that is. Yes, Dr. Walter.
I don't understand much of what you did. You know, I'm not on your plate. I didn't put your proposal. I didn't read your dissertation. So, um, so my question is generic. What in in which cases do you think this approach that uses uh, conversational systems, you know, LLMs, uh, is going to have an advantage over more traditional planners?
Uh, so traditional planners are a technique that we use along with like to achieve better conversational agents, goal-directed conversation with the end users. Are you pitting conversational
No,
assistant?
sorry, I used the term conversational systems in a bad way. I meant LLMs.
Okay.
So, when should I invest, if you like, in an LLM in addition to using a good standard plan?
Right. Especially when the action space that we are looking at is very huge, and the number of objects employed are very um, the environment itself is massive. It's a large scale environment. That's when using any neural approach, which can help bring in the inductive biases that were learned during training and generate a, I would not call a plan, but an output much quickly that symbolic planners can use as a heuristic to build upon, is what both can work together on. I don't think, I mean, both of them have their drawbacks in certain things when it comes to that. So large language models alone will not suffice, and planners alone will not solve all the problems. But the problems that planners can solve, they do it very well. And if we are looking at solving all kinds of problems, especially with large number of objects or action space, they still solve them, but within a stipulated amount of time, it becomes hard for them to solve it. So that's where LLMs can come, because complexity is not a criteria for them to generate an output. They can generate a bogus output, but they would still generate it much quicker. Now, we as AI practitioners can pick up what is an useful part of that bogus output and actually pass it as a heuristic for the actual planner to build upon. So there is some guidance that is quickly coming, and the planner builds on top of that to solve a particular plan.
So is a human in the loop component here?
I mean, just there is no human in the loop explicitly. The entire the process of doing this is end-to-end automated. So how the LLM interacts with the downstream planner is end-to-end automated, but the human has to tweak and play around with a set of hyperparameters to find the right coordination between them both in order for the performance that we want to see. Thank you so much for the question. Yeah.
Collaborative assistance for information flow. There was a system 1, system 2.
Right.
The system 2 is more sensitive. So what's the trigger for going to system 2?
I thought I did not have the time, so I skipped through the pipeline. But so we are actually looking at the risk of the question to begin with. Then we have a whole sort of we begin with starting at looking at the risk that the question poses itself, and this is being done using a keyword match in guidance with the EU AI Act, the European AI Act. And once we have the risk assessment for the question, we have the metacognition pipeline deliberate on the prior performance of system 1, the correctness of the system 1 in the prior iterations, in order to deliberate whether it can use system 1 or it has to fall back to using system 2 as the actual source for generating an answer. Yeah, so in the memory, we store all past occurrences which system solved for a particular question correctly. So we use that information use that information in the sense it's used as prompt context when we are passing to the LLM. We retrieve top 2 relevant question answer pairs from it.
You know, the committee can answer questions. Yeah. Online, yeah, both meeting online or?
You have 3 committee members, Amit, Leon, and Sharon.
Okay. So maybe we can start with the meeting and teams if you have any questions.
Should you just take a 2 minutes break, let everyone go?
Oh, sure. Yeah. If you want to stop in the morning.
Yes. Yeah.
Let's stop the record.
So the plan